Hi, and welcome for another episode of Quadratic Sieve running on Java. My name is Ilya Gazman. Let's hack. During the last episode, we entered the mini optimization phase. Those are small hacks with big impacts. So more of those small candies are coming up today as well. I will quickly talk about all of the optimizations that I did today, and then we will see them in details in the source code. So for Siever, I merged it with VectorExtractor. To create a better resource balance in the system, I placed the VectorExtractor on the same thread as the Siever. Replace double with bytes, that's a cool one. It turns out that our bSmooth threshold becomes so big, so it's sufficient to use bytes instead of doubles. PolyMiner, cached MathUtils.modSqrt. The heaviest part of the PolyMiner is the composition of the wheels, and the mod square was responsible for about 60% of it. This is when we are doing the mod square of the prime. Calculated the delta sieve of the perfect range. Due to a rounding error in our A calculation, where A is that, and it's chosen to the closest integer to 2n divided by m, we ended up with a non-perfect range. So to fix it, I calculated the perfect range as that, and then the delta is equal to this. That's also a very cool thing, because now the values will be smaller, and hence the chances for finding bSmooth values increase. VectorExtractor. Fast 2 extraction. Since we are working in base 2, we can quickly extract all the 2 powers by checking the last set bit index, and then shift right to remove it. Both of the functions are available in the big integer, so it's easy and cool and nice. Due to all of those optimizations, I had to play again with the magic numbers. Not fun. I moved away from using b and switched into using the prime base size, which is more accurate. With a little bit guessing, a lot of guessing, I was able to find the combinations that yield 100% improvement in the overall speed. Okay, so let me show you the source code now. Go to Quadratic Sieve. So first of all, the merge of the VectorExtractor with the Siever. Now, in terms of the threads in the system, we have PolyMiner, metrics, and the Siever, where now I'm using the all available cores times 2 a number of threads for the Siever. It looks better in the performance. So let's start with the PolyMiner. For the PolyMiner, there is a new delta calculation happens over here, and it's sufficient to calculate it once for all the polynomials. The A is not changing much, so the delta is pretty good. This calculation is just what I showed you earlier, so it's that part and this part. And with this delta, we are now building the wheels. So the wheels are using delta in the pool. It's propagated to here. So now the starting position is being adjusted by that value, and the rest remains the same. Just rename starting position to current position. Okay, now the scale is cool as well. The scale belongs to the Siever. We're replacing doubles with bytes. So it helps with the conversion between double and byte, just multiply it by the scale, and then it's converted to a byte. And it's happening inside the PolyMiner scale calculation. So I'm taking the base log, which is based just on the delta, and then I'm dividing it by 4. So it's the largest values that we will get. And to work with, so that was supposed to be sufficient. But then when we need to solve how to compare negative and positive values, because values above 128 become negatives for bytes. By dividing it by 4, we're giving enough space and range to work only with positive values. So that's cool. All right. So we talk about the vector extractor merge into the Siever and how we switch working with bytes over doubles. Let me actually show you that in the Siever as well. For the Siever, when we are calculating the base log, we are using the scale. And base log is now byte instead of double. So that's super cool. Those are those two optimizations. In PolyMiner, I also cached this part. This is so small, but it was so impactful, which is insane. So during the build wheels, that takes over 90% of our overall performance of the PolyMiner. That area took 60% of the performance. And by doing that, it went below, I don't know, I didn't check, but very, very low. Map is a map between big integer to big integer, and we are mapping a prime to the mod square, to the result. Where x is actually better name would be a prime. But I cannot choose prime. P is taking. No, let's keep it x. But it's the prime. Okay. So we talked about those two. And finally, the vector extractor. A small but very cool optimization. So now extract, wait. So now it starts from here. We are doing the extract with all the smooth values that we collected from a single polynomial. Then extract has been called for each of those polynomials. And we are counting the time executing this method. And in here, this is our extract vector. The one thing that changed is that stacked power 2. So we have a lowest set bit method. And if it's greater than 0, it means that the value is divisible by 2, power lowest set bit. And what we are doing is just shifting right. Then if the lowest set bit is an odd value, we are updating the vector as well. And yeah, small optimization, but very powerful. And I think that's it. Let me show you the performance. So I saved a few executions. This is a funny one. So 140 bits, it's been among of our first executions, and now it takes less than a second. So it's super cool to see. For 200 bits in the last episode, we've been running 38 seconds. Now it takes only 17 and a half seconds. So we sliced the time by 2. The vector extractor works very close to the Siever. I've actually been playing with the magic numbers, and what I noticed, if we include the small primes, we are getting much more big primes values. So it gets those pretty much swap. We are getting more big primes than completely bSmooth values. And then the vector extractor becomes the heaviest part, which is awesome because now we have one thread for both the Siever and the vector extractor. So in terms of the resource balance in the system, it's good. Looks like we're going to jump a lot between the one to another, especially now that it's so easy to change it just playing with the magic numbers. So yeah, I also executed a few other results. So this is for 220 bits, 120 versus 278, so more than 2 times faster. And next challenge, yeah, 240 bits. It's nice that the system is capable of making this factorization. It takes 414 seconds. Um, the matrix is pretty fast. Vector extractor, yeah, works less than the Siever. Yeah, and the values are pretty similar. Okay, if you have any questions, please ask me in the Facebook group or comment below. And the source code is going to be available in GitHub. See ya.